Okay guys, in this video lesson we're going to start talking about the different things that determine how electric circuits flow and how they work and the energy that they contain and the power they have. Okay, to do that we want to first start to talk to you guys about this kind of table. And what we see here is all the different things that we're going to talk about in the next 3 or 4 days. All right, we've already introduced what charge is, what its symbol is, the units it uses, and the unit symbol. Okay, we know time from before. Current's going to be new to us. Current's going to be symbolized with an I, and the unit we're going to use for that is going to be the amperes. A lot of times we shorten that down and just say the amps for that. Potential or electric potential, we use the capital V for volts. Resistance is a capital R, that's measured in ohms. And then power, again, is one that we're comfortable with already. That's our P for watts and W. This table will become useful later on as we combine everything together, because it's often I find that students, when they're learning about wattage and voltage and ohms and amps and current and potentials, they get these things confused. So this is a place you can go back to see a nice grid system of how everything all aligns with each other. Okay, so here we go. First thing we want to talk about is the electric potential. All right, we've seen this animation before, but we want to pull it up again because it does a really good job of showing us what we mean about electric potential. Okay, when you have electric potential, that's the amount of electrical energy the electrons have at any point given in a circuit. So it is a type of potential energy. So it is the potential for them to do work for us, but electric work instead. Okay. Now, typically we think of a battery having an unbalanced charge in it, and that battery then allows current to flow through a circuit. Okay, as that battery sends electrons out, these are positive charge, but same idea here. As that sends current flowing through your circuit, you have high potential to start. And then what happens is, as you run it through some sort of resistor or some sort of device, whether it be a light, a phone, a speaker, something that you are powering, it uses that potential energy to power that device, and then those things return back and then stay there or get reused if you have an actual thing, a source to like recharge that battery or so forth. Okay, so the idea here is that the electrons contain potential energy, and those electrons then are able to give that potential energy to the device to be able to use it. All right, they can transfer that energy to run the devices. Okay, which means at any given 2 points on a circuit, electrons can have a different amount of potential energy. Okay, which means that they don't have the same energy at all times or all places. All right. Now, one way that we visualize this idea of electric potential is as a waterfall. All right. So we think of a waterfall. At the top of the waterfall, there's lots of potential for the water to fall down. As it falls, it loses that potential, and it goes down. It lands in the splash pool, and then goes down the river, however it goes. Okay. Same idea for the electrons. They start off with high energy, or the top of the waterfall, and as they fall, they lose their electrical energy to the device, and at the bottom, they don't have that anymore. Okay. We talk about having a tall waterfall is like having lots of electric potential, versus a short waterfall is having low potential, or having high energy versus low energy. Okay, it's just a way for us to visualize electric potential, because electrons are not something that we can visualize very well. All right. Now, when we actually measure electric potential, the way we do that is the difference of those potentials. We do that through what's called voltage. Okay, so when you have a difference in potential across a circuit, we measure that by taking the change in our energy that we have divided by the charge that's there, okay? Or we measure the volts of something, okay? You've probably heard of volts before. For example, like AA batteries and AAA batteries, they are a 1.5 volt battery, okay? Typical iPhones of this era run about 3.8 volts. So that's just the amount of energy that they utilize per coulomb of charge that they have as you run that device. Okay, a household circuit has 110 volts. So that is something that we use in our house. It's a different type of circuit, but it's the same idea there. That's the potential difference that it uses as it runs that energy through the circuit. Okay. Now this is per coulomb of charge, okay? So we see that our units here are joules per coulomb for our volts, right? Now keeping that in mind, how many joules of energy are available in a 9-volt battery for each coulomb of charge, okay? So if we have a 9-volt battery, so it's 9 volts here, and we want that per coulomb, So the available energy then would be just 9 joules of energy. So we get 9 joules of energy out of every coulomb of charge in a 9-volt battery. Now the question becomes, well, how many coulombs of charge do we have? Okay. Well, the conversation about how many coulombs of charge are available or how much coulombs of charge flows through the circuit is a different topic. That's going to bring us down to the world of current and amps and that kind of stuff. So for now, we want to limit this to this idea of what is the available energy that we have in volts, joules per coulomb here. Okay? All right, that's actually going to end the video lesson here. In our next lesson, we'll get into the next step of this, which is current flow. Thank you.